Hi guys, in this video we're going to continue with chapter 2.6 and we're going to look at problem 282 in the 14th edition. Okay, let me just bring the textbook close. So what do we have here? Okay, so we're going to look at 282 in the 14th edition. It says, three forces act on the ring. Okay, so here we have the diagram. Again, remember, positive x-axis in this direction, positive y, positive z. Okay? It says three forces act on the ring. Here we have a ring and we've got three forces. We have F1 here, F1 equal to 80 Newton, acting there. We'll get into more details later. F2 is 110 Newton, down in the negative z direction. Then we've got F3, which is unknown. We don't have any information regarding F3. And then they give us the resultant force. They give us the magnitude and then these angles here. Okay? So you can pause the video and you can study that diagram if you don't have the textbook. Okay? And the question is, if the resultant force Fr has a magnitude and direction as shown, determine the magnitude and coordinate direction angles of force F3. Again, it says, if the resultant force Fr has a magnitude and direction, it has a magnitude of 120, and it has a direction as shown, right, it's got these angles, determine the magnitude and coordinate direction angles of F3. The magnitude of F3 and its coordinate direction angles. Okay. So I've tried my best to draw this. Okay, so what do we have here? We've got. I mean, perhaps I can try to bring the camera a bit closer. Perhaps that might be a bit better. Okay, I think that's a bit better. Okay, so guys, what we have here is we've got F1. F2 and F3, and these three forces give us a resultant Fr. Okay, now I just want to write this down first in vector form. Maybe I can do it right next to it here. Fr in vector form equals what? It equals F1 plus F2 plus F3. Okay. We really should be clear about this by now, that adding up these three forces means we're adding up three vectors, okay? And then we have a resultant force vector, okay? So now, what would you say is the first step for us to do? Well, remember what we've been trying to do in the last few videos is we're trying to convert these forces into Cartesian vector form. Okay, so let's just start by doing that, and then we can come back to this governing equation here. Okay, this vector equation. So what is Fr? How do we write Fr in Cartesian vector form? First of all, what we need to see here is that Fr is given to us. We're given a magnitude of 120. That's the magnitude. But then we are given these angles, and based on what we've been learning, what are these angles known as? Well, they really are the azimuth and the transverse angles, right? These angles that they have given to us are not the coordinate direction angles. Okay, they're based on the transverse and azimuth angle. Okay, so although that actually there, the angle between that force, that vector and the positive z-axis, actually that is the azimuth angle, phi, but they've given us the complementary angle, 45 degrees. This 45 degrees is the angle between the force, this force Fr, and the xy plane. Okay? So, maybe I'll just do an arrow there because I'm not in the position yet to write equals. So what would we say? Okay, hold on. Let me redo this. Fr in vector form, Cartesian vector form, is frx in the I plus fry in the j plus frz in the k. Newton. So how do we determine these three components? Well, let's look straight away at frz because that is always the easiest and the quickest. Frz is actually this component here. Can you guys see that? Frz is this vertical component. It's basically the component along the z-axis. So how do we calculate that? That's going to be the magnitude, which is 120 sine of 45. Okay? So is that clear? That is equal to 120 sine of 45 Newton. I just want to check with my notes if that's correct. Yes, okay? Then, so now we've got frz, okay? We've got frz here. Frz is 120 sine of 45 because can you see that that is a right angle triangle there? That is our angle. There's our magnitude. So 120 sine of 45 gives us that vertical component. But now we also need frx and fry. So what do we need to do? We need to first get this component along the xy plane, right? So we can call this fr dashed. Okay? So what is fr? Fr dashed is simply the 120, it's that magnitude there, times cos of 45. Okay? So that's our first step. So there's our frz. We've got that. We're happy. But now we're trying to find frx and fry. But in order to get frx and fry, we first have to get that component right there. And that component fr dashed is equal to 120 cos 45. So then frx is then equal to fr dashed, it's equal to that value there, or that component there, times the sine of 30. Sine of 30. Why the sine of 30? Because that triangle on the floor, I call the floor the xy plane the floor. Then we've got the magnitude fr dash. The sine of 30 gives us that component there, which is then the x component. And then fry is equal to fr dash, that component, right? So cos 30. So it'll be the fr dashed, which is this component there. Cos of 30 gives us the y component. Okay, then just further developing it, fr dashed is then 120 cos 45 and then sine 30. So fr dashed is the 120 cos 45 and then we still multiply by the sine 30. And then we've got your 120 cos 45 times cos 30. Alright. Which then this equals 40, let's check here, 42,4 Newton. And this equals 73,5 Newton. And this frz equals 84,8 Newton. So now, if we want to write out fr in Cartesian vector form, what is our x? Our x is 42,4, so we've got 42,4 in the I plus 73,5 in the j plus 84,8 in the k Newton. Okay, so that's our first step. We've now converted this force Fr into Cartesian vector form. Alright, now what about F1? Let's have a look at F1. F1 is equal to F1x in the I direction plus F1y in the j, and plus F1z in the k direction, Newton. So that means we have to determine F1x, F1y, F1z. Now if we look at this drawing, right, and if you go back to the much better drawing in the textbook, you'll see that this force is acting in the xz plane, the xz plane. It has no y component. Can you see that? It's acting in the xz plane. Its magnitude is 80, and it's got this triangle here, the 5, 4, 3 triangle, which allows us then to calculate the components. Okay? So what would F1x be? F1x would be what? It would be the magnitude of this line, which is 80, times, let me just see if I've got the diagram correct. Yes, times 4 over 5, right? So it would be 80 times 4 over 5 Newton, which equals, let me just see my calculations here, equals 64 Newton. My F1y would equal 0, right? And my F1z would equal 80 times 3 over 5, because it's the z component. 3 over 5 Newton, which equals 48 Newton. So F1 in Cartesian vector form is then equal to 64I plus, just for completion, I'm going to say 0j, just for completion, plus 48k Newton. Alright, so now we've got FR in Cartesian vector form, we've got F1 in Cartesian vector form, and what about F2? F2 is relatively straightforward, because F2 is just acting in the z direction and the negative z direction with a magnitude of 110. 110. Okay? So what is F2? It is minus 110k Newton. Alright. So we've got the resultant force, we've got F1 in Cartesian vector form, and we've got F2 in Cartesian vector form. So remember, this is what we're after. This governing equation will allow us to calculate the unknown F3. Alright, so let's move on. Let's turn the page. Okay, so again, let's try and get this page. If I write out FR, again, is equal to F1 plus F2 plus F3 in vector form, right? So FR is equal to what? What is our FR? It is equal to 42,8I plus 73,5J plus 84,8K equals F1, which is 64I plus 48K. That's my F1. Remember, the J component is 0. Then minus 110K. That's my F2. Remember, that's my F2 there. F2 has no I and J component. And then we add F3x in the I plus F3y in the J plus F3z in the K. And obviously that there is my F3. So FR in vector form should equal F1 Cartesian vector plus F2 in Cartesian vector form plus F3 in Cartesian vector form. Okay, So from what we've done before, how would we then solve for our unknown F3s? Well, we would just equate the different components, x, y, and z. So this would be FR on our left-hand side, and this would be F1 plus F2 plus F3. Just a reminder that the governing equation is this. It's F, the resultant force is equal to the sum of all the forces, right? That's really what we're looking at here. The resultant force is equal to the sum of all the forces in vector form, okay? So what are all the components in the x direction for FR? We have 42,8, right? 42,8 equals, now what, do we have any x for the F1? Yes. Or any components in the I direction for F1? Yes, we've got 64. Okay. We have 64. We've got no x component or anything in the I direction for F2, so that's 0. And then we've got an F3x, so we've got F3x there. Okay? Then what about the y direction? Well, we've got 73,5 is equal to 48, no, that's wrong. Equal to, straight away, F3y. On the right-hand side, the only y components is that. The only y component is that. And then we've got our z component is 84,8 is equal to 48, right? 48 minus 110 plus F3z. Okay. So we've got those three equations. If we end up solving now, let's solve for those three, because now we're going to solve for F3x, F3y, and F3z. F3x equals minus 21,2 Newton. Okay? I'll make a comment now on that specifically. F3y is equal to 73,5 Newton, and F3z is equal to 146,8 Newton. All right. So we've got these three. Now I just want you to notice something here. We've calculated a force, F3x, to be minus 21,2 Newton. Okay? So just a small little point here, that a force really, I don't really think you can call a force negative, but what we need to see is that a force is acting in a negative direction. If we choose a certain direction to be positive, and we calculate this minus 21,2, then it means that the F3x is actually acting in the negative direction along the x-axis. Okay, but nevertheless, we have now calculated each one of these F3 components. So basically, if we write out F3 in Cartesian vector form, we are going to get minus 21,2i plus 73,5j plus 146,8k Newton. All right, is everyone happy with that? But now, so what is the magnitude now of this? How do we calculate the magnitude? F3 is equal to minus 21,2 squared plus 73,5 squared plus 146,8 squared square root. That gives us 165,5 Newton. Okay, I'm just going to use this value in the rest of the calculations. Okay, so now, remember the question was what is the magnitude and coordinate direction angle? So now we've calculated the magnitude. Okay, we've calculated the magnitude. Now what about the coordinate direction angles? Guys, how do we calculate the coordinate direction angles? We use we can use our direction cosines. What are they again? Cos of alpha is equal to f3x over f3. That's the component of along the x direction divided by the magnitude of f3. We've got cos of beta, which equals f3y over f3, and we've got cos of gamma equal to f3z over f3. So cos of alpha is equal to what? What is f3x? It is minus 21,2 over the magnitude 165,5. Then cos of beta is equal to 73,5 over 165,5, and cos gamma is equal to what? It's equal to 146,8 divided by 165,5. Alpha then gives us 97,4 degrees. Beta gives us 63,6 degrees. And gamma gives us 27,5 degrees. Okay. So we have our magnitude, 165,5, and we've got our three angles. Okay. So now, when you look at these angles now, and if you really do understand what these coordinate direction angles are, what does this tell you then about? Let's say we draw this now, okay? And I'm just going to draw. Okay, there's Z, there's X, there's Y, and here is F. Okay, F3 rather, F3, and it's got an alpha of 97,4 degrees. It's got a beta of 63,6, and it's got a gamma of 27,5. Now I just want you to think about this and see how this corresponds to the x, y, and z components which we calculated. Right? There's my x, my y, and my z. Does this make sense? Is this answer correct? Right? I should have my x component was minus 21,2. My y component, f3x. My f3y is 73,5, and my f3z is 146,8. Guys, does this make sense? Just think about it. Look at my fz. It's a positive number. Is my z value positive z? Yes. My f3y, right? Is that in the positive direction? Yes, because my angle is less than 90 degrees. If beta was more than 90 degrees, then this force would be on that side, and it would give me a negative y component. Okay? But now look at x. Look at f3x. I have a negative x component, meaning that it's landing on the negative side along the negative side of the x-axis, and my alpha is greater than 90 degrees. So does that make sense? Yes. If alpha was smaller than 90, somewhere inside the 90 degree, then this f3x should be positive. But because alpha is larger than 90, it is landing on that side, so we have a negative x component. So please try to look at this critically and see if your angle plus your values correspond. Okay, I hope this helps. Thanks a lot.